Okay, good evening, everybody. I hope everybody can see me on the last short band, but if you cannot see me, you can hear me at least. So, I'm going to report on two experiments of 112 and 114, which we have performed in order to measure the transition strength of first excited Hooker state. Now, one of these experiments were performed at Inter-University Accelerator Center, New Delhi. This is my home institute, and I'm presently work on behalf of IUSC New Delhi and GSI Germany. Okay, let us start with a little introduction to the very interesting tin region. We know that this is the longest isotopic chain between two doubly magic nuclei. We have 100 tin on one side, 132 tin on one side. And when we fill these shells, we fill G7 half, D5 by 2, S half, D3 by 2, and H11 by 2. And we do this when we move from 100 tin towards 132 tin. This is a typical level scheme of a tin region. This is for 112 tin. And this is a typical structure of CNOD scheme. So we have this G7 half shell, which we fill in the case of 120, and we can populate all the possible states up to 6 plus. As we know, G half, another G half, one cannot reach in 7 plus. So the highest spin which can be populated is a 6 plus state, and this is an isomeric state, and this is the half-life. Our aim is to measure the lifetime, or you can say the transition strength of the 2 plus state, and this we can perform with the help of Coulomb excitation, because in the case of the fusion reaction, the lifetime of the 2 plus state is governed by this, the lifetime of this isomeric state. So this is the process, the reaction mechanism which has to be used in this case. So let us have an overall view about the tin region. As you can see that the 2 plus and the 4 plus energy is almost no change, and this is a typical behavior of generalized CNOD scheme. And in this picture you see it is B2s are produced against the mass number, and what you expect is a nice bell-shaped back structure. And for doubly magic 110 and 120 and 132 tin, the values are 0, and maximum is expected around mid-shell 116 tin. Now here is the experimental data before we performed our experiments, and what we notice here basically, okay, the two nuclei of our interest are 114 and 120. These are the last two stable isotopes on this tin, tin range. And the thing to be seen here is that if you look at all these experimental values toward the neutron-rich side, they are very well matching this bell-shaped like structure. But after the mid-shell, when you go towards the neutron-deficient side, there is an enhancement in the P2 values. So this is the question which we can ask ourselves, that does these two nuclei is going to follow the trend of high P2 values or not? So experiments, there were two experiments which were performed. One at IUSC New Delhi, 412 tin, and another one at GSI, 414 tin. This is a typical setup for the experiment which was performed at my home institute, Inter-University Accelerator Center, New Delhi. We have taken 58 nickel beam of energy 175 MeV. We have, in the backward direction, we had germanium blower detectors. This is our target, and in the forward direction, we have the planet counter. In both the experiments, the reference was this flashing number, the P2 value for 116 tin, which is supposed to be very, very precise, because this is an evaluation from 14 different experiments before we perform our experiment. And here the few details are, okay, in this way we normalize with 116 tin, and we try to get rid of almost all the error bars. Few details about the parallel plate counter. So this is the same reactor which was used in both the experiments, and phi information is obtained from the anode foil, which has 20 segment of 18 degree each, and theta information is obtained from the delay line. Okay, at GSI we have taken the tin beam on nickel target, and the particle identification was done with the parallel plate counter. Here, what we can see here is the static dependence on time of flight, and one can clearly distinguish between the nickel and the tin ions. When you get on nickel, you can do the Doppler shift correction for the projectile acceleration as well as for the nickel acceleration. It can be another way around also. You can get on 140. And these are the results from IUSC, where we have nickel beam on highly enriched thin targets, and Doppler corrected target excitation and the projectile excitation is shown in the corrected spectra here. And here also the tin intensity is normalized to the nickel intensity. Okay, the data analysis is done with respect to this transparency. We have B2 values from nuclear data tables, precise values I just discussed. of 116 or 58 nickel. And there are two possible ways to determine these B2 values. The first one is just to normalize with 58 nickel. The second one is to normalize with 116 tin. And in the second case, you have to perform two experiments, and then the ratio of 58 nickel cancels. And the other important part about this second part of determining the B2 is that the first excited energy state, energy of the 2 plus state of 114 tin and 116 are very close by. So this is what we have chosen is we have done our determination of B2 using the second way, and this is cross section, and we have not only used 0 to 2 plus but also the contribution for higher rank states were taken into account. So now the results. This is a picture which I just shown you a few minutes back, the experimental data before we did our experiment, and now we replace these with the points which we have, the measurements which we have performed. So this is for 114 tin and this is for 112. So we have reduced the error bars, but what we can see here that still there is an enhancement in the B2 value. So this trend is still continuing here. After the results, we can compare our results with the theoretical calculations. First we can compare it with the shell model calculation. As we can see that the shell model calculation does not show this asymmetry, neither with 100 tin core where you have only free neutrons and you choose an effective charge of 1, nor with 90 tin core where you have not only neutrons but also the free protons, and you change the effective charge to 0.5 and 1 here. And what observed is the enhancement on this neutron deficit side, and also these values are supported very well with the values of 106 and 110. The other theory with which we can compare this is relativistic quasi-particle random phase approximation. As you know, in these calculations, they do not depend on any effective charge, no core is required, and also they have given very satisfactory results for other isotopic chain like nickel and lead. So what we see, we observe a higher B2, I mean the B2s are going up as it is here, but still there is a little band in the absolute B2 value over here. So this is my conclusion slide before I thank my collaborator and organizers. So these are the newly measured B2 values for 112 and 114 tin. This is the experimental data with theory. And now I would like to draw your attention toward the label scheme of tin region. Now if you draw a line on the mid shell 116, and if you look at the neutron rich side, we have only H11 by 2 shell filled. But when we go towards the lighter side, we see that there is a mixture of H11 by 2, D5 by 2 and G7 half. And that might be the reason for this enhancement in the B2 value. But this is still an open question to be answered yet. And where we go from here, we do not stop here, okay, we just continue our investigation, and there will be experiment on 114 using the pre-spec setup at DSI in very near future. I thank all my collaborators. The experiment performed at IUAC New Delhi and at GSI, and all the names which are on this slide. Thank you very much to make this both experiments successfully. I'd also like to thank the organizers for inviting me to give this short talk on a nice place like this, where you have really good time in the evening to go out and do whatever you feel like. Maybe it is a bungee jumping. Thank you very much.